Welcome everyone to the first afternoon session of CAMLIS. I have the pleasure today to introduce Bayan. So what can I say about Bayan? Well, first, he's a multi-year CAMLIS speaker. He's spoken here before. But he's also jointly training a dog and a 1-year-old. Currently, the dog is the better performer. And with that, Bayan.
Hello. Do I have to speak into this thing? Yeah. Okay. A few more things about me. I am a machine learning engineer. I work in the applied research group at Capital One's Center for Machine Learning. I don't actually spend very much time working on cyber use cases in my day-to-day job. I've worked a little bit in cyber in the past. Mostly I focus on graph representation learning, and I thought that this would be an interesting application of it. And I have presented at CAMLIS in the past, so I thought let's see if you guys were interested. And it turns out that there was some interest in learning more about it. So I'm going to talk a little bit about it today. So the topic is applying deep graph representation learning to the malware graph. So my introductory slides are basically the same as several other introductory slides that you've already seen today. There's a lot of malware out there. It's a very important business problem. There's a lot of variance in the data, so you have variance on the same specimens. It creates a need to identify if a piece of malware is similar to other pieces of malware. So we've all heard this a lot today, and the scale is very, very large. So that's kind of the technical problem. And we think about like some of the machine learning techniques we've heard about already today, and what we know about machine learning for malware is that traditionally, it relies on features that you can quantify at the individual sample level, right? You want to know some set of things about each piece of malware so that you can pass it into some system that either learns how to classify it or cluster it, etc. But what we also know is that there is this kind of rich set of overlapping components that make up each of the malware. And binaries in general don't live on their own. They have connections to a lot of other things out there. And so that is often left on the table when you collapse everything down to an individual feature set per sample. And at the same time, the traditional ML solutions, it's very difficult to induce similarity at scale on new samples. So some of the cool stuff we learned earlier about joint embeddings of malware with tags, I think, was trying to solve that problem also, is how do you induce how do you determine for a new thing what is it similar to that you've already seen? Like that's a big challenge for a lot of these systems. So the tack that I sought to apply for this is graph machine learning to malware. And so kind of a brief agenda of what I'm going to talk about today. I'm going to explain what graph representation learning is, because not everybody's going to be familiar with that. Talk about how you can think of malware as a graph, or define graphs over sets of malware, and then I'll talk about applying graph representation to malware graphs, and then finally talk a little bit about some future directions in this research. So first things first, this is a graph. So a graph can be defined as, it's kind of a network. We've seen this before. It has edges and vertices. Vertices are the nodes in the graph. They're the little circles. Edges are the lines that connect it. I think we're all fairly familiar with what graphs are. There are a lot of different types of graphs. Some of the common breakdowns in what a graph is, you have directed and undirected graphs, meaning directed meaning that edges can point in specific directions from nodes to other nodes. Undirected means that the direction doesn't matter between them. You can traverse that edge in either direction. You have weighted and unweighted graphs. And a weighted graph, it's basically placing some extra piece of information on each of the edges that determine the strength of the relationship between those two nodes. And then finally, and there's a lot of other types of graphs. These are just a few examples of types of graphs. Finally, there's attributed graphs. So this is a graph where you might have specific attributes about each of the nodes in your graph. You can also have attributes about the edges beyond just the weight of the edges. Some common graph properties that you probably want to know about. The degree. So the degree of a graph, or the degree of a node, is the number of edges that node has. The density is the relationship between the total number of edges in the graph to the number of nodes in the graph. And finally, we have communities. So in this case, you can see communities are kind of the color coding of the different nodes in the graph. They represent subgroups within a graph that can correspond to a number of properties. So we heard about Louvain detection on a graph earlier. That's a way of identifying communities in a graph. And so there's a lot of different ways of representing a graph. One common way is an edge list. So this is just two columns. One is both of them represent nodes, and then the fact that the nodes appear in this edge list defines the fact that there's a relationship between those nodes. Another way is an adjacency matrix. So an adjacency matrix, that same graph that I showed earlier, now you have a matrix that is the size of the number of nodes you have by the size of the number of nodes you have, and it's just a 0 or 1, a 1 defining whether or not there is an edge between those two nodes. Another common way of representing a graph is a Laplacian. So this is an unnormalized Laplacian. The Laplacian is you take the adjacency matrix, which is this, and you take the degree matrix, which is basically just the diagonal of the matrix. And on that diagonal is the degree of each of those nodes. So A has a degree of 3, B has a degree of 3, C has a degree of 3, D has a degree of 4, and E has a degree of 3. And you subtract the adjacency matrix from the degree matrix. And so that's just another way of representing the information of your graph in a numerical form. And so why do we want to represent informations of our graph in a numerical form? Is obviously, in order to do machine learning, you can't do, I'll just jump back a little bit, you can't do machine learning directly on a graph, right? It's a set of entities. You can't even do it on an edge list. You need to transform it into something that you can use for a machine learning task. And in order to do that, you have to make it a numerical form. And so these are some traditional ways of representing a graph. If you're familiar with NLP, some of the traditional ways you might represent words in a language model was a one-hot encoding. It's kind of a similar way of approaching it. But as you can see, one of the problems with these types of representations of graphs is, A, they're very sparse, but B, as the size of your graph gets very big, they become really, really tricky to handle, right? We're talking, if you have 1 million nodes, you now have a 1,000,000 by 1,000,000 matrix that you have to pass into your machine learning model, and that's not particularly useful. It's also tremendously sparse on very large graphs. So most of it's going to be zeros, with a very small subset being ones, and so that's not easy to deal with. So that brings us to graph representation learning. Graph representation learning it's a set of unsupervised, sometimes semi-supervised machine learning techniques for taking that graph that you have and projecting it into a lower dimensional space, a lower dimensional continuous space, in such a way that you preserve key graph properties. One of the most common ways of thinking about that is if you take a graph and you have two nodes that are neighboring on the graph, or there's an edge between those two nodes, when you project them into a continuous space, the distance, the Euclidean distance, or the cosine similarity between those two nodes should be very, very small. So that's the idea of graph representation learning. And here's an example. So on the top we have the graph, and then on the bottom we have an embedding of that graph. We have a representation learning algorithm that's been placed on that, and you can see now it's gone from this thing that has no real numerical information, it's now in 2 dimensions. And you can see that the things of the similar color, the things where you have edges on the graph between them, retain their distance to one another. And so some of the structure, the neighborhood of the nodes in the original graph are now in this 2-dimensional space. And you might be wondering, why would you need that? Well, now that you have these vectors for each of your nodes, the vector just in this case being an x and y coordinate, you can do things like node classification. You can do things like clustering and search. You can do community detection in the continuous space instead of having to do it on the graph itself. You can do anomaly detection. You can say, is there an edge, would I expect there an edge to be between these two nodes in my graph? And so how do you do this? One of the common ways to do this is what's referred to as shallow random walk embeddings. So if you're all familiar with Word2Vec, it's a common way of taking language and encoding it in a low-dimensional space. You can do something very similar with graphs. And so in a language model like Word2Vec, you have sequences of words that are in a document, and you embed those words based on what other words they co-occur with. you can generalize that to sequences of nodes on a graph. And so the way that you get those sequences of nodes on a graph, the most simple way to do that is to generate a bunch of random walks on your graph. So you just pick a node to start at. In this case, we start at A. We traverse that edge. We get to C, then D, then E. And that is one of the sequences that we could feed into one of these Word2Vec style models. Do that again for starting at node B, D, and B, and E. And you feed that into a standard skipgram model, which is a single layer neural network model that says, given a node in my graph, predict the other nodes that are nearby it. And in doing that task over and over again on lots and lots of sequences in your graph, it learns this low-dimensional representation of each of the nodes to make that prediction most accurate. So basically to be able to predict what neighborhood a node resides in accurately. So that's the very simple version. And then there's a slightly more complex variant of this that has come out in the last few years, where instead of a single layer skipgram model, you might want to apply popular filter mechanisms and pooling mechanisms that we've learned in convolutional neural networks that are good for images. You might want to apply that to neighborhoods around a node in your graph. So you're going to pull in information first from your immediate neighbors, and then from maybe an order out beyond that, and then you're going to figure out how to aggregate that information to generate a node representation for each of the nodes in your graph that most accurately encodes the neighborhood. The nice thing about some of these deeper graph embeddings is you can also do this in semi-supervised and fully supervised settings, meaning that if you have a label for each of your nodes, you can directly learn a representation for the node that more accurately predicts that label. So let's talk a little bit about how you create a graph. There are obviously natural graphs in the world. There are things like social networks. Those are very easy to understand as a graph, but you can also turn anything into a graph if you really want to. It's true. But what makes a good graph? Typically, you want to create a graph in a situation where you have relationships that are many to many, where you have variable sets of things that are connected, and those relationships are defined by some kind of semantic or meaningful set of information. In order to define a good graph, you also want to be able to easily generate new nodes in that graph. You want to be able to easily compute where the edges should be on the graph. And finally, you don't want to just take something that you could very easily have as a node attribute and make that an edge on your graph, because if it's very easily represented as a node attribute or as an individual data point, it's not really worthwhile making that an edge on the graph. So for malware, a couple of things that you could do. This is a very limited list of ways to define edges for malware. Like I said, I don't have a background in cybersecurity, so I'm sure the list is much longer for people who are experts. One way you could define edges are DLL imports or Yara matches between two files, and that's using static analysis, and then dynamic analysis. You can look at IP calls, contacted domains. Any number of these things can define edges between samples of malware. Additionally, you can have node attributes. I think we all know the many myriad node attributes that you can have for individual samples of malware. So now once you've defined a graph and attributed the nodes, now you can learn, you can apply one of these representation learning algorithms to it. So here's an example, and this is the example that I'm going to kind of build on as showing how this might work, which is here we have, this is really a tripartite graph. So we have three different types of nodes in this graph. I believe the purple are your actual samples, and the teal color, if you can't see that, those would represent DLLs, and then the darker blue would represent actual function imports for each of the files. Okay, good. And so, as you can see, there's this many-to-many relationship. You can think of the function imports as kind of the building blocks for each of the samples. So this is an interesting way to say, okay, if I want to know what the corresponding overlap of the files that use the same sets of function imports, then I could encode this graph. Now, it's very hard to do graph representation on heterogeneous graphs. Heterogeneous meaning you have different node entity types. You typically want to apply this to homogeneous graphs. So you want to collapse this down to a single entity type. So the way that you would do that in the case of this particular example is you would take and you would define an edge between any two samples where they import the same function from the same DLL. And you would apply weight to that edge for the number of overlapping imports that they have. And so this is an example of taking that across a number of samples and projecting it down. And in this particular case, the color code actually represents, if you take the, getting back to some of the tagging that they were talking about earlier, if you take some of that and you cluster the tag names, so there's just a way of kind of visually representing like overlapping clusters in terms of how it's been labeled. You can see that there's quite a bit of heterogeneity. There's 25 different classes of tag names that we've assigned here, and the communities don't necessarily map to them perfectly, but there are some clusters in there. One more thing to identify about this particular graph that I'm going to show you how we embedded it is here is something. This is the node degree distribution of the graph. And you can see it's a very strange node degree distribution. There are a number of samples with extremely high degrees, meaning that they are connected to almost every other sample, or many of the other samples. And then there's kind of a valley, and then there's a number of nodes with degrees around 1,500 to 2,000, and then it drops off from there. Those types of degree distributions can be challenging. In this case, it didn't actually present a significant challenge, but as your system scales, very high degree nodes can actually present challenges to some of these, and I'd be happy to talk to you about that later. So, took that graph that I showed you.
That huge peak, is that just a huge clique?
Yes, so those are all connected to each other. Exactly. And you can kind of see it. There's this one here. There's actually two main clicks. There's this thing here. And you'll see that in the results actually. So we take that graph and we want to say, okay, learn low dimensional representations of that graph. So the three different tasks you might want to do with graph representation learning. So you might want to do node clustering. So in this case, how well does the graph recover some original topology? Or how well does the embedding recover some original topology of the graph? And then you might want to do node induction. So for a node that you've never seen before in your training algorithm, where would you expect it to reside within your embedding space? And then finally, in the supervised setting, node classification. Can you assign a label to a node given its position just in the embedding space? So in the node clustering setting, so these both represent t-SNE plots of the embedding dimension for all of the nodes. So you can see, as you pointed out, there were two big clicks. That comes up very clearly in the embedding space, both for the shallow random walk embeddings and for the deep graph embeddings. But then you also see some of the other communities start to arise out of these embeddings in both of these. They both recover kind of similar structures when you do this. One thing to point out is that with deep graph embedding, there's a lot of different variants that you can do. With the shallow random walk embeddings, there's only really one way to do it. With the deep graph embedding, you can do it without any node attributes. You can just take the graph as is and embed it. You can also add in node attributes. You can add in the file size. You can add in all of that other information. And what you start to see is that the structure changes according to some of that information. You start to get more heterogeneity in some of the communities in terms of which labels they might have. And so that's one of the benefits of doing deep graph embedding is your lower space can capture more structure and more nuance about the graph that you have. And then finally, if you do that deep graph embedding and you add in the label that you had for it, the virus total label in this case, as one of the attributes that you're trying to encode, it actually nicely starts to segment your graph. It learns the lower representation that kind of picks up the fact that you have different labels in different communities. And so then we get to node induction, and here's a plot that you can't see. I'm sorry about that. I can walk you through it though. So what we have here is a test node. So this is a node that you don't have in your training graph. So you take a graph, you remove some of the nodes from that graph, and those are going to be your test nodes. You embed the training graph, and then you want to train a secondary model that says, okay, given some set of neighboring nodes in the training graph, predict the location of a node. So you train a secondary model that can predict position of a node that you've given it. And so that model then says, okay, given which other nodes this is connected to, we predict that it sits right here in the embedding space. And these are its nearest neighbors in the embedding space based on just distance. And so it predicts a location for it that's right here. Its actual graph neighbors. Oh, thank you. Its actual graph neighbors are these teal ones. So you can see some of them these are actual graph neighbors also. They're just the nearest of them. You can see some of them are quite far away, but it predicted that the closest ones are right there. And then non-neighbors, this is just a random smattering of other nodes in the graph that aren't connected to that node. So you can see that it picks a point in the embedding space closest to these 7 or 8 nodes, but that's equally far from a lot of its non-neighbors. So it induces a position that's correct. On the node induction task, one of the common ways that you can measure how well you're doing node induction is something called mean reciprocal rank. So it's basically the position in the rank order that you generate when you say, give me the nearest neighbors for this particular node. When you use one of the shallow random walk embeddings, in this case I'm calling it deep walk, which is the name of the paper that came from, it performs well, but you can see that increasingly, both in terms of mean reciprocal rank and link prediction, so that's a different task. That's saying, given a node and you've induced it in a position, can you predict its immediate neighbors in that embedding space? Both mean reciprocal rank and link prediction task gets better as you add the deep graph embeddings, and then also as you start to add in the features. So in this case, you see a significant improvement with the deep graph embeddings, and then adding in the features gets your best score. And then finally, for node classification, so 2 scores here. So this is basically, I talked about the classes. So we took all the possible virus total labels and we clustered them into 25 groupings of labels. And so this is a classification task trying to recover whatever the grouping that was assigned to that node. And so the baseline here is a random guess, so it's basically a 1 out of 25 score, both for micro and macro F1. Whereas when you do the shallow random walk-based embeddings, you get a significant performance improvement over the baseline in terms of micro F1, but a slight degradation in terms of macro F1, whereas for the deep one, you get an improvement both in micro and macro. And I think am I out of time? I've got one more slide. Is that okay? All right. So, this is some preliminary research into how you can apply some of these techniques to malware. Some of the next steps are, can we add more dynamic attributes instead of just the static ones that were included? Benchmark against more common solutions, scale to much larger graphs. So I showed you this was a small graph. And then incorporate more attributes and more edge types would be another thing that we want to try next.
All right, cool. I'd like to ask if we have any questions. We do have the microphone to pass around, and I guess we can start with Keegan.
Great talk. 2 questions. Your title, I noticed it didn't include a joke or a pun of any kind. Are you feeling okay?
Yeah.
Okay, I have a real question. Early on when you showed the original tripartite graph, at least for a couple of the samples you showed, they seem to form very disconnected components. If we think of this as like a total graph, sort of each file and who it connects to could be quite disparate from this one.
Yeah.
When we think about supervised learning on graphs, it's almost always node classification, right?
Yep.
Each node has a label. There's a much smaller set of applications around, here's an entire graph, give me a classification of it, which is more similar to vision, right? Here's an image,
Yes.
give me a classification of it. Some of the only examples I can think of have been applied to biochemistry and like molecular physics, where it's like, here's a molecule, which I can represent as a graph over the periodic table of different elements that are connected to each other, and then can we predict the biochemical properties of it? Do you think that would be useful here, where you can say, here's a file and connections to it, let's look at that as a graph, and then let me do some classification on that using a graph neural network?
Yeah, absolutely. And so the idea would be then for every file you would just have the tree of all the things that it imports, and maybe a single classification just for that particular file, and then you train a model to make that prediction
Over the set of all such graphs you've ever seen before, yeah.
I mean, you could absolutely do that. I think I'm not sure if in those models they actually learn a node level representation, or if they just learn a full graph level representation in order to make that predictive task. But maybe that's all you need, because at the end of the day, the graph that you're defining is for each sample. And so if you have a graph level representation of that entire thing, it is a sample level representation.
Awesome.
Thanks very much. Great talk, thank you. A lot of the language that you use, like low dimensional representation, low rank approximation, cosine similarity, all of this implies to me modeling by an SVD. Now, sometimes using neural networks, it sort of sucks you into possibly dismissing or ignoring what are possibly older techniques.
Sure.
What thoughts do you have about applying an SVD? Because that language matches singular value decomposition precisely.
Yes. And so a lot of times, if we go back to the graph Laplacian, which was this guy, I'm going to jump back quite a bit, this one. Some of the very early work in graph representation learning was applying SVD directly to a normalized graph Laplacian. It was something called Laplacian eigenmaps. Yeah, you've read that. And so that's exactly what they do. They find they find an eigenvector for each of the nodes in the graph. Those struggle to scale to very large graphs is one of the challenges with them. The other challenge with them, at least for, I'm actually not entirely sure for graphs, but I know this in the language space, so I can say that, is when you do SVD, you can't have zeros in the matrix, right? So you'll typically see something where they shift the matrix and add a 1 to all the places where there's a 0, because you get this infinity score that you can't actually use over all the zeros. And if you think about what that does in a graph, where you have zeros in the adjacency matrix, if you were just to apply SVD to that, you'd essentially be creating edges where there are no edges. Right? You're saying things are related. There's this baseline connectivity between everything in the graph. And then some things are connected more than others. But that's not entirely a good way of looking at your graph, right? You actually care about the zeros, right? You care about the things that don't have connections. And in fact, you don't just care about the things that don't have connections. You care about the things that really don't have connections, the things that are far, far away from each other on the graph. That's actually one of the challenges that the adjacency matrix by itself doesn't really tell you, is that, like, actually there's a much longer distance between this red dot over here and this purple dot than it would imply by just having a 0 between them. And so some of these neural-based systems, what they do is they generate noise samples. They create a noise distribution over non-edges and sample from that distribution. And by the random walking is generating the sequences of edges you looked at, but for every single node, you're also going to sample from a noise distribution of nodes. And so that forces the model not just to learn things that are connected, but learn things that are not connected in specific ways.
Do we have any other questions? I think we have time for one more. And that actually works out well.
So this was a great talk. Thank you very much. Couple of quick questions. One is, does the embedding necessarily retain the centrality matrix of the graph?
That's a great question. I don't know. And in fact, we're actively doing some research into specifically what properties of the graph the embeddings retain. Our hypothesis is that different algorithms retain different properties to differing degrees. And so one way that you can do that is to train secondary models that seek to recover certain properties and see how well you do at recovering those properties as a way of quantifying the efficacy of your representation learning model.
So the original cost function does not implicitly account for...
No.
Thanks. And my second question is, how computationally efficient this process is?
So for the shallow random walks, it's incredibly efficient and very scalable because you're only looking at small chunks of sequences of these random walks that you've pre-computed. So assuming you can easily generate random walks, there are ways to approximate that at scale. Then the remainder of it is it's a very shallow network. It's one layer. It's a linear projection essentially into your embedding space.
How do you compare the deep approach to a regular deep classifier? The computational cost of it, of course.
In terms of a regular deep classifier, well, it's at the end of the day, it's not any different. It's how you get the data into the model that varies depending on whether you're looking at geometric structures versus Euclidean structures, right? And so that computationally that can vary quite a bit because you have to apply a number of sampling techniques because essentially you want to pull in the neighbors of every single node and make a classification on that node. How you sample that neighborhood can have impacts on the performance of the model, both in terms of accuracy but also in terms of computational cost.
Thanks.
All right, let's everybody give Bayan another round of applause.